Okay, sorry for the technical problems, and we'll try to start with this talk. So I'm glad to introduce Jounghoo Lee that will present the work of GCoM, a digital GPU core modeling for accurate analysis, a analytical model for modern GPUs. As far as I understand, Mr. Lee is about to graduate and looking for a postdoc or position, so you are welcome to approach him after the talk, and we'll be very glad to hear new opportunities.
Okay, hello everyone. I'm Jounghoo Lee from Yonsei University. I'm glad to present GCoM, a detailed GPU core model for accurate analytical modeling of modern GPUs. To find the best hardware design for various softwares, architects must optimize and test a lot of parameters in early design stage. However, the cycle level simulator, such as XLSim, which was the de facto standard architecture evaluation tool, is too slow. It takes all day long. So it is an inappropriate choice for early design space exploration. Analytical model can greatly help computer architects by performing design space exploration orders of magnitude faster. MDM, the state-of-the-art GPU analytical model, promises more than 6,000 times faster hardware evaluation speed. Using interval analysis, it can not only predict the performance, but also build cycle per instruction stack. The CPI stack provides us latency breakdown to various stall events and give us deep insight. The key idea of interval analysis is that a WAP scheduler could maintain its maximum issue rate until a stall event occurs. An interval consists of a sequence of instructions with the maximum issue rate and the stall cycles. The model selects a representative WAP and evaluates expected stall events at the WAP scheduler. First, the data dependency divides a single WAP into intervals. Then multiple WAPs hide the latency, exploiting the WAP level parallelism. Additional memory contention stalls are considered afterward. Note that these procedures are based on MDM. Accounting the different latency for each type of instructions, interval analysis model the stalls incurred by data dependency. It uses the average memory access time by cache simulator along with the fixed arithmetic operation latency. The data dependency chain among WAP instructions splits the single WAP execution timeline into intervals. Then the model derives SM execution timeline with multiple WAPs by WAP scheduling policy such as greedy than oldest. Finally, the memory contention at the interconnect network and DRAM is considered, assuming that all the SMs operate identically. MDM counts the number of cache line requests per interval. Then it quantifies additional stalls by request with the miss ratio from cache simulator. To apply the interval analysis to modern GPU, we try to simply adjust the tunable parameters of existing model MDM. The issue rate can represent multiple WAP schedulers at the SM, and several new functional units can be represented with its latency. Unfortunately, it still suffers from large modeling error with modern GPUs. CPI stack compared to the Excel same cycle level simulator shows that MDM underestimate compute structural stall, and it also underrate memory structure stall and overestimate memory data stall, and it does not model idle stalls at all. We found that naive modeling has such error because of their outdated and highly abstracted GPU core microarchitecture assumption. First, MDM does not consider the subcores and the resulting compute structural stalls. A modern GPU SM can issue multiple WAP instructions per cycle, but an SM partitions its computational resources into subcores. The limited functional unit length can incur compute structural stall as it now takes more than one cycle to issue an instruction. Second, at the SM level, each multi-bank Aaron data cache is now shared between multiple subcores. The Aaron data cache may induce memory structural stalls, and it contradicts the assumption of the MDM that Aaron data cache have infinite hit bandwidth. Third, that Aaron data cache is now sectored, which splits each cache line into multiple sectors sharing the same tag. It can alter the memory data stores significantly by accessing L2 cache and DRAM in sector granularity. Let's see the example when 4 threads in the WAP access 4-byte memory with 60-byte stride. Assuming the cache is cold, non-sectored cache fetches 2 whole cache lines from the L2 cache. In contrast, sectored cache fetches only the necessary sectors, reducing the memory traffic to half in this case. Additionally, MDM cannot capture the idle stalls by load imbalance between the subcores. The multi-issue WAP scheduler cannot incur any load imbalance. Lastly, with increasing SM count, the load imbalance between SMs occurs more frequently. However, MDM cannot capture resulting idle stall. They assume all the SMs operate identically, executing the same number of WAPs. To summarize, we could not simply extend MDM because of outdated and highly abstracted GPU core model. First, at subcore level, they do not take into account the limited functional unit lanes per subcore. Second, at the SM level, they are unaware of banked and sectored Aaron data cache. Also, they do not consider load imbalance inside the SM. At the GPU level, it cannot take into account different load between the SMs. To tackle down the limitations, we propose GCoM, a GPU core model that faithfully captures the core size stall event of modern GPU. GCoM resolves challenges by hierarchical microarchitecture-driven core modeling upon the existing interval analysis. First, at the subcore level, GCoM introduces different initiation interval per functional unit. At the SM level, GCoM estimates the effective Aaron data cache bandwidth per interval. GCoM extends each cache simulator to model sectored cache, and it estimates WAP level parallelism at every subcore. Lastly, at the GPU level, GCoM counts the number of WAPs executed by SM, considering the thread block scheduling policy. GCoM quantifies the compute structural stall caused by the limited functional unit lanes per subcore. The idea is that longest functional unit determines the issue cycle of the interval. With respect to the functional unit lane count, GCoM applies the different initiation interval. For example, 2 for int and 8 for special function unit. When a subcore executes 2 WAPs with an int and special function unit, stall cycles incurred by special function unit hide that of the int unit. And compute structural stall of an interval are approximate to the difference between special function unit issue cycle and minimum issue cycle when WAP scheduler issued an instruction. GCoM repeats this for subcores in the SM without the inactive ones. At the SM level, GCoM models memory structural stalls. It calculates the effective Aaron bandwidth with bank access pattern of the representative WAP. GCoM uses the memory access address of each thread in the WAP to determine the per bank access count regarding a coalescing scheme. As the slowest functional unit hides stalls of the other, memory structural stall can hide compute structural stall. The difference between minimum issue cycle and error data cache access are assumed to be memory structure stall of the SM. The whole data cache access and each instruction issues are assumed to be fully parallelizable. GCoM can consider both sectored and non-sectored cache using its cache simulator. The simulator can count the hit miss count per sector and evict per line by LRU policy. It can also coalesce memory accesses by sector. By doing so, memory contention model exploited from MDM could use correct amount of bandwidth demand to predict memory data stalls. GCoM estimate latency hiding by WAP level parallelism at every subcore, which has been done at the SM before. WAPs at the other subcores cannot hide the data stalls because they do not share functional unit lanes. Consequently, the number of WAPs executed by SM may differ, and also the subcore active cycles. GCoM calculates the idle stalls as the difference between one subcore and the longest running one belonging to the same SM. Finally, GCoM adds all stalls together and gets the per SM active cycle. GCoM estimates the number of WAPs on SM execute following the thread block scheduling policy, such as round robin. The Intel SM load imbalance can then be considered by comparing active cycles of each SM. The corner cycle stacks are calculated by averaging SM cycles. GCoM builds the aforementioned analytical models for each hierarchy of microarchitecture at subcore level, SM level, and GPU level. For more detail, please refer to our paper. And this is end-to-end GCoM framework, which applies new analytical models upon MDM. GCoM uses a CUDA application and hardware parameters as the input. GCoM collects the SASS trace and select the representative WAP and apply single and multi-WAP model like prior work. And the subcore level model and SM model of GCoM calculates the compute structural stall, memory structure stall, and intra-SM idle stalls as explained. Note that cache simulator is modified beforehand to estimate correct amount of memory data stall. Finally, GPU level model estimate the inter-SM idle stalls and generate corner cycle stacks. Now I will present the experiment setup to evaluate GCoM, followed by the result and a conclusion of this talk. We evaluate GCoM by comparing its performance prediction with MDM and by using XLSIM as the ground truth. We employed GPU stall classification method proposed in GPU stall inspector to build CPI stack. We configured XLSIM, MDM, and GCoM to model a Turing-based NVIDIA RTX 2060. We used 31 representative GPU applications. GCoM significantly improves the accuracy by achieving mean absolute percentage error of 10% against XLSIM with each cycle prediction, but MDM suffers from nearly 45%. In terms of CPI stack generation, GCoM achieves cosine similarity higher than 0.9, while MDM suffers from 0.7. GCoM accomplished it by correctly modeling the core size stall events. For example, only GCoM can capture the compute structural stall of Rodinia backpropagation. MDM misidentifies primary bottleneck as the memory data stall because it does not model subcore stalls. Using the accurate and detailed GPU core model, GCoM can perform various design space exploration. Here is two examples. As the number of subcores per SM and SM count changes, GCoM closely follows the XLSIM and capture the primary bottleneck, while MDM cannot. Ultimately, a GPU analytical model should faithfully reflect the performance characteristic of a real GPU. In this sense, we validated GCoM against NVIDIA RTX 2060, 2060 Super, and 3070 GPU. The results show that GCoM achieves a mean absolute percentage error of 24.4% against RTX 2060, which is comparable to the Excel sim. The cycle correlation against real GPUs are also similar to the cycle correlation of the Excel sim. Additionally, the trace collection process is time-consuming. GCoM could efficiently model the different NVIDIA GPUs using the trace collected from an NVIDIA RTX 2060 GPU. In conclusion, we propose GCoM, which accurately captured the key core size stall event of modern GPUs. GCoM targets hierarchical modeling of core microarchitecture, which has been overlooked by existing GPU analytical models. Our evaluation shows that the GCoM greatly improves the accuracy over prior works by achieving mean absolute percentage error of 10% against Excel sim and 24.4% against RTX 2060. Also, GCoM is nearly 350 times faster than the Excel sim. Thank you for listening, and I would be glad to answer any questions.
Thank you very much. We are a little bit out behind schedule, so one question if okay, can you check if somebody on the line wants to ask something? Yeah. And the next speaker, please approach the podium.
Thank you for the great talk. I just wonder how are you going to capture or model the contention of the network on chip, between SMs and the cache banks?
Okay, that's a great question. For the interconnect network and DRAM contention, as I mentioned, we employed the great work of the MDM, which is the prior work.
Okay, thank you very much. And all other questions, please email to the authors. And as I said before, I think that you are looking for a new position or a postdoc, so please approach him after the talk. Thank you very much.
Thank you.
So now we'll try to go to the videos again. We hope to be lucky this time.
Hi everyone, I'm Sedaghati, a Master of Science graduate student, and I'm also open to work. Today I'm going to present our toolchain Xcache. This was a joint research at Simon Fraser University under supervision of my advisor Arrvindh Shriraman. So before I dive into the presentation, I'm going to give a quick summary of our research. So the key observation that we made during this research was that emerging DSAs work with index data structures. It means that they have to handle non-affine data structures, pointer chasing, dynamic accesses, and irregular access patterns. So the main challenges are that, first of all, they have to know how to capture the reuse and how to orchestrate the data movement. That's why we're proposing Xcache, a portable cache template for DSAs. Our two main contributions are that, first of all, we're using DSA fields for tagging data on. Hi everyone, I'm Sedaghati, a Master of Science graduate student, and I'm also open to work. Today I'm going to present our toolchain Xcache. This was a joint research at Simon Fraser University under supervision of my advisor Arrvindh Shriraman. So before I dive into the presentation, I'm going to give a quick summary of our research. So the key observation that we made during this research was that emerging DSAs work with index data structures. It means that they have to handle non-affine data structures, pointer chasing, dynamic accesses, and irregular access patterns. So the main challenges are that, first of all, they have to know how to capture the reuse and how to orchestrate the data movement. That's why we're proposing Xcache, a portable cache template for DSAs. Our two main contributions are that, first of all, we're using DSA fields for tagging data on chip instead of the global addresses. And when there's a hit, we do not need to walk the data structure. And we're integrating cache walkers with the cache controllers. Also, the cache controller will be programmable as well. So the output of our research is that we have a toolchain for generating cache RTL for different DSAs, which can be accessed via this link. And in terms of the evaluation, we reached 1.7 times better performance, 50% lower power, and 2 to 8 times lower bandwidth usage than an address-based conventional cache. So this is the outline of this presentation. At first, I'll go over the challenges in designing an SPMM DSA, and then I'll cover our toolchain Xcache, and at the end, I'll go over the evaluation of our research. So let's start with building an SPMM accelerator. First of all, it's working with the sparse matrices stored in the CSR format, both submatrices. And the algorithm is simple. We choose one element from matrix A, we multiply it by the corresponding row in matrix B, we go to the next element, and we multiply it by the corresponding row in the matrix B as well. And then we merge the outputs. It's a Gustafson algorithm. So what are the challenges for targeting this DSA? First of all, as I said, matrix A is using A and B, and similarly, matrix element O is using the same elements again. So we have to have a mechanism to capture these kind of reusings. So we have to replace the on-chip SRAM with a cache. Actually, all of the DSAs that we explored are using a caching structure in their design. The second challenge is that now we have to cope with non-affine data structures. And by non-affine data structures, we mean that, similar to this demonstration, for getting the data that we require, we have to read some portion of the data first, another portion of the matrix, get some indices or pointers, and based on those information, go and fetch the data that we need. Same thing as this example. we have to read the row pointer operator first, get 2 pointers, and based on that, go and read the column and value vectors. So the challenge here is that instead of streaming in bulk and tiled data, we have to break the accesses into smaller pieces, and it means that there's a higher chance for underutilizing the DRAM bandwidths. The next challenge is that we have to work with dynamic accesses. And by that, we mean for getting some values from matrix B, for example, we have to read matrix A first, go to a part of matrix B, and based on that, go and read the data that we have to fetch. So we have to have several steps of traversing different data structures for just maybe getting one single element, similar to here. For getting values A and B, we have to go through 2 vectors of matrix A, and then 1 vector of matrix B, and then to the value vector of matrix B. Then for getting just one single value, D from matrix B, we have to do the exact same steps. The same challenge again. Instead of streaming in tiled bulk data, we have to break the accesses into smaller, and in this case, dependent accesses. So that's why we're introducing Xcache. We have 3 main ideas behind this toolchain. The first one is that we're replacing address tags with meta tags. We're integrating DSA walkers into our cache controller, and we're using a coroutine-based execution model. So, about the first idea. As I said before, DSAs work with DSA fields, row and column in this example. On the other hand, DRAM and cache work with global addresses. So we always have to do some address translation or even address generation for getting the value that we need. It means that even when the data is already on chip, when it's a hit, we have to do this translation or generation again. So the address tags are not capable of recognizing whether it's a hit or not without those extra steps. That's why we're using meta tags instead of the address tags. So basically, we're using the same DSA fields for tagging the data in the cache, and now DSA can directly use the same information for reading from the cache. The second idea is that we're integrating the walkers into the cache controller. So when there's a miss, we have to go and traverse the DRAM. We have to walk it. But now the onus of walking is completely on the Xcache. Xcache is in charge of issuing walkers, maintaining them, and the data orchestration. And the DSA data path is completely decoupled from these tasks. And the third idea is that we're adding programmability to our cache controller. So let's take a look at these examples. On the top, we have inner product algorithm. So we're choosing one row of matrix A, and we're multiplying it by a column of matrix B. At the bottom, we have the same example that I showed before. We're choosing one element, we're multiplying by a row, we're choosing another element, and we're multiplying it by the corresponding row again. So as you see, within 2 DSAs that's working with the same DSA fields, row and column here, and even doing the same functionality, matrix multiplication in this case, we might have different walking logics. So that's why we're having programmable walkers in our design. So we're able to target a wide range of DSAs. And also, within this programmability, we're breaking down the walkers into smaller routines. So Xcache now can issue multiple parallel coroutines at the same time. So this is the toolchain of Xcache. The programmer is in charge of programming meta tag fields, defining them, and in charge of defining walking logic. We pass these meta tag fields to our chisel generator. And at the end, we have a Verilog for our Xcache. Then we compile down the walking logic into microcoded actions. We load it on the Verilog of the Xcache, and at the end, we have a domain-specific cache. So Xcache is a toolchain for generating meta tag arrays and DSA cache internals, programming cache controllers for data orchestration, and parameterizing cache controllers for different DSAs. So this is the overview of microarchitecture of Xcache, and for explaining this microarchitecture, I'll be using this example. This is similar to traversing a bucket inside a hash table. We go node by node until we reach a node that its key matches our input key. So the first block in our microarchitecture is meta tag memory, and it's simply a mapping between meta tags and the location of data inside the data memory. In the same example that I showed before, let's say that we cached 14. The next time that we're going to access the same node, we can bypass the walking. We do not need to go over 10, then 23, and then 14. We can directly access node 14 and read it from the data memory. The next module is our walking state machine. So we break down our walking logic into smaller parts called routine, and each routine consists of a sequence of actions. And for calling different routines, we're using a table-based state machine. And that's how we embed our walking logic inside our cache controller. So let's say that in this example, instead of having a long walking logic similar to this code, we can break it down into smaller pieces. Each block is one routine, and basically this gives us our walking logic inside the Xcache. The next module is our active walkers. So in the same example that I showed before, we have to generate the address of a node. We have to read it from DRAM and then do the comparison. But when we're waiting for the data to come back from the DRAM, we can allocate an entry inside our active walker, release all of the other resources, and then wait for the data. When the data is back, we will read that entry and we can proceed from that point on. So this also helps us having a table for active walkers to maintain multiple walkers at the same time. The next module is our action executors. So this basically execute our microcoded actions, which are the building blocks of our routines. And also the number of executors can be determined by the user. So we can execute multiple parallel walkers at the same time. And the last module is the data memory, and the number of way and the set of it can be defined by the user as well. For evaluation, we use the cycle accurate RTL simulator for evaluating Xcache, and we also synthesize the generated RTL on FPGA. We used 5 different DSAs for evaluating Xcache, and in terms of the performance, we delivered 1.7 times higher performance than address-based caches, and 50% higher in comparison with customized on-chip SRAMs of some of these DSAs. Also, in terms of the bandwidths, we use 2 to 8 times lower bandwidths than an address-based cache, but by just not walking when there's a hit. And in terms of the power, we use 25 to 80% lower power than an address-based cache, and meta tags only used 7% of the total power usage of Xcache, and programmable controller only added 6% to the power usage of Xcache. Thank you so much. I'll be here for answering your questions.
Thank you. Uh, okay, so this is Jing from the University of Illinois at Urbana-Champaign. So nice talk, first of all. I really appreciate our work. So what I'm wondering is, so if, for example, like a heterogeneous system, then do you require all the hardware pieces like the CPU, GPU, and also your accelerators to be written in this X-cache orchestration? This is my first question. And my second question is, if the answer is yes, then what is the area, extra area overhead you're adding to this whole system? Because I noticed that you have the performance and the power numbers, but you don't have the area numbers. So those are my questions. Thank you.
Okay, yeah. Can you hear me? Okay, so the answer to your first question is yes. Yeah, as long as the user can issue metal loads, the type of loads that the Xcache work with, yes, they can work with different type of the users, CPU or even GPU or even a customized RTL on FPGA. And in terms of your second question, we have some number in our paper, but we evaluated this and we use OpenRoad for synthesizing it. And in terms of the area, so we executed it for number of executors equal to 8 and number of active walkers equal to 16. And so the area, the cost of area wasn't that much. And the numbers are in our paper as well.
Hi everyone, this is Sudhanshu from Intel Power Labs. I would be presenting raster file prefetching. This work was done with my colleagues Sumeet, Jayesh and Shri. Most of us would already know the fact that modern this memory wall has been to prefetch data closer to the cores in these on-chip caches. Now, because DRAM has the highest latency, most of the past research has been focused on prefetching from the DRAM, whereas small caches like L1 are not considered to be an issue because of their small latency. We tried to quantify the performance headroom of prefetching between the different levels of cache and memory hierarchy. Our results show that prefetching from memory into the last level caches leads to a huge 13% performance uplift. This large performance gain from prefetching into the last level cache is expected given the high latency of DRAM. What is more interesting is the last column of the chart, which shows the performance headroom of prefetching from L1 data cache to the register file. Much to our surprise, prefetching from L1 to the register file has very similar performance headroom as prefetching from the memory, even though the latency of the L1 data cache is just 5 cycles. This performance headroom becomes more apparent once we realize that 93% of all loads hit the L1 data cache. This is why it is critical to mitigate even the small L1 cache access latency. Moving forward in this talk, I will start by discussing prior works like load value and address prediction, which can be used to mitigate the load latency. Then I will present our work on raster file prefetching, which targets mitigating the L1 cache latency. Further, before concluding this talk, I will present results from experimental study which evaluate our proposal. Let's start with the first set of prior works which perform value prediction, or more specifically load value prediction. These schemes work by predicting the value of a load. This predicted value is then used by load dependents to execute independently of the load, thus allowing processors to hide the full latency of a load from its dependents. The main drawback of value prediction is that it results in a costly pipeline flushes when the prediction is incorrect. Value prediction hence needs very high accuracy, which in turn reduces the overall coverage. The second set of prior works use address prediction to perform value prediction. They exploit the observation that load addresses can be more predictable than load values. While the load instruction is being fetched and decoded in the front end, the load address is predicted. This predicted address is used to probe values from data caches. Further, if the probe can be completed before load allocation, the probed value is used to perform value prediction. Unfortunately, the front-end slack for probing data caches is decreasing due to fetch latency optimizations like UOP cache, which limit the overall coverage of these schemes. Further, in-flight stores limit probing the data caches to avoid flushes. Moreover, the loads need to refetch the value from data caches to validate predictions on load execution. In summary, load value prediction is not very helpful at mitigating the L1 latency, as its primary target is to increase instruction level parallelism. Further, it suffers from coverage and costly flushes. We hence propose register file prefetching, a true prefetcher which prefetches data from the L1 cache into the register file. Moreover, our proposal does not suffer from costly pipeline flushes. Before discussing how register file prefetching mitigates the L1 cache latency, I briefly present how a load and its dependent are scheduled in a traditional out-of-order pipeline. This would set the stage for register file prefetching. In this figure, the load I4 is allocated in cycle 1 and starts its execution in cycle 5 with its address computation, followed by L1 data cache access in cycle 6 to 9. There is a minimum of 3 cycle delay between a UOPS allocation and its execution because of the multi-cycle speculative wake up and select issue stages. Now, to get the load dependent to start its execution in cycle 10, when the load data is expected to be available, the load dependent must be woken up in cycle 7. Here, the execution of the load dependent is delayed and it suffers from the full L1 cache access latency of the load. Now consider a scenario where the load value has been prefetched and was available in the register file when the dependent is allocated. When such prefetching is performed, the dependent can execute without waiting for the load to complete, thus hiding the load's L1 access latency. This is what we are trying to achieve with register file prefetching. Okay. Register file prefetching works by predicting the address of demand loads. It launches a prefetch to the L1 data cache. However, the value in the L1 data cache can be stale due to in-flight stores which write to the predicted address. In such cases, the value prefetched from the L1 data cache would not be correct even when the address is correct. Therefore, prefetches must probe the store buffer to locate the correct value. This means that they can only be issued after the allocation of the demand load, so that all older in-flight stores are visible to the prefetch. This would guarantee the prefetched data to be correct if the address is correct. We saw in the last slide that there is a 3-cycle issue slack in the out-of-order pipeline. This slack is what we exploit to prefetch the data just in time. Okay. To summarize, RFP issues prefetches at load allocation. These prefetches are opportunistically executed in the load pipeline. They cam against in-flight stores to obtain the most recent value. By doing this, the prefetched value is guaranteed to be correct if the address was correct. This further allows us to validate the prediction by just comparing the prefetch address with the actual load address. Finally, the prefetched value is written in the same register file entry as the demand load. This allows the dependents to take the data from the existing register file pipeline, and we don't have to do any modifications to the out of order pipeline. Further, to the memory unit, prefetches look like the corresponding demand loads and are not reordered across memory barrier. This guarantees memory consistency and correctness. Register file prefetching is a true prefetcher. It does not cause pipeline flushes in case of incorrect predictions. This is achieved by making dependents execute only after the prefetch address has been validated to be correct on the load's execution. The top pipeline schedule here shows a case where the prefetch has completed in cycle 1. In cycle 5, when the load address is computed, we see that the prefetch was incorrect. In such cases, the speculative issue of the load dependent is cancelled. Note that the dependent was only speculatively issued and had not yet executed. Thus, no pipeline flush is needed. Further, the lower pipeline schedule shows a similar case where in cycle 5, the demand load address is computed. We find that the prefetching was correct. In these cases, the speculative issue of the load dependent continues. This allows the dependent to execute with the correct prefetched value, which was already available in the register file because of the earlier prefetch. Overall, we see that there are no costly pipeline flushes with RFP. Thus, we can make it very aggressive and increase coverage. We evaluate RFP on a Tiger Lake-like system using 65 diverse single-threaded applications, which include all the Spec 17 applications. This chart shows that RFP improves performance by 3% on a Tiger Lake-like baseline. We also see 43% of all loads are successfully prefetched. For these loads, the prefetch address was correct and the prefetch hides the L1 cache access latency. This chart shows that prefetch packets were generated for 72% of all loads, but prefetches for only 48% of all loads were executed and completed. Prefetches get cancelled when they are not able to launch before the demand loads execution. This is because L1 bandwidth is constrained and prefetches opportunistically use the available L1 bandwidth. To further increase coverage, solutions are needed to increase the available L1 bandwidth. Finally, we see prefetches for 43% of all loads were correct and helpful in hiding the load latency. Only prefetches for only 5% of loads were incorrect. Note that these incorrect prefetches do not cause pipeline flushes, but only reissue the dependent in the out of order pipeline. This chart compares the performance from RFP against value prediction. We use the composite value predictor that combines both the value and the address prediction schemes we discussed earlier. As shown, RFP improves on the composite value predictor. Moreover, clubbing RFP with value prediction provides the highest performance. Here, value predictor helps improve ILP, whereas RFP mitigates the L1 latency of the non-value predicted loads. Finally, we conclude that future cores would need to mitigate the L1 cache access latency. We proposed a prefetcher, register file prefetching, that prefetches from L1 cache into the register file. Our prefetcher successfully prefetches 43% of all loads into register file and improves performance by 3% through the mitigation of the L1 cache latency. This concludes our talk. Thank you.
Okay, let's ask the question.
Yes, thank you. A great talk, Manoj Kumar from IBM. You kind of implied that the stall comes on when the dependent instruction to the load is just executing very nearby the load instruction. But in modern CPUs, where you have a large number of instructions in flight, in excess of 100, why is the compiler not able to put a distance between the load and the dependent instructions?
A good question. So basically, most of the time, these dependencies are through memory address and they are irregular in nature. And the compiler does not know about these at the application compilation time. So it is not able to kind of detect these dependencies as compilation time and not able to separate them. Yeah.
Forsgard, University of Edinburgh. Cool talk, cool work. So I'm guessing from your technique that you're seeing very high hit rates in the L1 for the prefetch. That is to say, the addresses you're prefetching are highly predictable. I'm wondering if you have any thoughts about that. I mean, one suspicion, one guess I have is that these are stack accesses, right? And so that's where a lot of the benefit of prefetching is coming from, is the stack. Comments, thoughts?
So as I mentioned in the slides that we see almost 93% hit rate in the L1 caches for the applications that we evaluated. So I mean, 93% that should include most of the stack and other addresses, memory addresses also apart from the stack. So it seems to most of the addresses are actually being hit in the L1 cache, are being read from the L1 cache, and this RFP prefetcher saves on the L1, the load execution pipeline latency, not specifically the L1 access latency. Yeah, I hope that answers your question.
Just make sure that you share. Okay. So the last talk we have for this session is coming from Toronto and Huawei, and it's on scalable architecture for a reprioritized ordered parallelism. The floor is yours.
Okay. Okay. Hello. Hi. Oh, we're still in echo. Hello. Okay. Hi. I'm Gil from the University of Toronto, and I'm here to tell you about techniques for parallelizing priority queues. This is a joint work with my collaborators
Yanzu, Dr. Guowei Zhang, and Professor Mark Jeffrey. So many important algorithms use a priority queue to schedule their task. That is, they look a bit like this. They enqueue some number of tasks into a priority queue, and then they dequeue and run the highest priority task repeatedly until the queue is empty. Some of these algorithms, like SSSP, can run their tasks in any order. The priority order allows them to do the least work in order to get the right answer, but they could do any order. In this case, the priority schedule is providing fast convergence. For other algorithms, though, the priority order is a direct part of the algorithm. For example, executing your tasks and adding edges in a random order will not find you a minimum spanning forest, but using a priority order will. In these cases, the priority schedule is part of the algorithm. While priority order tasks are a powerful tool for many classic and emerging algorithms, they are quite challenging to parallelize, especially when the priorities themselves are dynamic. In this paper, we present Hive, the first hardware-software system to extract speculative parallelism from priority updates. We achieve this by recognizing the scheduler dependence, an unusual class of dependence which occurs when tasks in a priority queue update each other. By applying speculation techniques to scheduler dependencies, in addition to the common data and control, Hive is able to achieve over 100x speedups over parallel software alone, and up to 2.8x speedups over the swarm architecture, which is prior speculative hardware. Now, we're going to be talking a lot about priority updates. So to begin with, we are going to walk through an algorithm that depends on them. The K-core algorithm for graphs analytics originated as an heuristic for graph coloring, and it can be used as a metric for importance of vertices. You can see the cores in the graph on the bottom left. To find the K-cores in a graph, we peel it, which means we repeatedly remove the lowest degree vertex and update the degrees of all of its neighbors. This algorithm will start by enqueuing all of its vertices into a priority queue with priority equal to their degree, and then repeatedly removing the lowest degree vertex. This we call a task. As an example, let's run the algorithm for this input graph. The task graph on the bottom right shows the priority of all of its vertices, and the cornice of a vertex is a priority which it ends up dequeuing at. We'll start by dequeuing the blue vertices E and F. Doing this reduces the degree and priority of a yellow vertex D to 1. And we'll then dequeue vertex D, which now also has priority 1, and reduce the priority of vertex C to 2. Finally, we'll dequeue vertices A, B, and C with priority 2. As you can see, the K-core algorithm is fairly simple, but it also depends completely on updating the position of objects in its priority queue. The question here is, where can we find parallelism in K-core? Well, there are 3 techniques for extracting parallelism from priority queues. The first is a bulk synchronous approach, where we execute equal priority tasks in parallel. We can see that there's some bulk synchronous parallelism here, but also that it's limited. Our vertex D only became priority 1 after we had processed vertices E and F with priority 1. This limits our ability to extract parallelism. In fact, in K-cores, almost the majority of vertices will execute alone between barriers. Another approach is to relax our priority queue, which means that we allow tasks to execute out of order and make an effort to execute them in order. Relaxation can always find parallelism, but as systems scale, it loses efficiency, and more importantly for K-core, it's not always correct. For K-core, if we relax our priority queue, we can get the wrong answer for vertices C and D, so relaxation is simply not an option here. And finally, there's speculation. Speculation techniques allow tasks to execute in any order, like relaxation. However, we monitor their dependencies and detect violations in order to abort misspeculating tasks. Doing this allows us to always find parallelism while maintaining the strict ordering that algorithms like K-core require. However, software speculative techniques have high overheads, and hardware techniques currently lack the ability to understand priority updates. Our goal in this work is to support an updatable priority queue in speculative hardware. The previous state of the art for task-based speculative parallelism in hardware is the swarm architecture. Swarm programs consist of short timestamp tasks which use an enqueue operation to convey new tasks to hardware. These tasks will appear to execute in timestamp order, And Swarm's hardware gives the illusion that they are being dequeued from a single sequential queue, but in reality, they are executing speculatively and out of order. Swarm's programs only call an enqueue operation. Their dequeues are all handled by the runtime, and no other operations exist. What this means is that Swarm does not support the priority updates that K-Core requires. We can still implement a version of K-Core in Swarm, though, but it will have some inefficiencies. Let's see how we do that. To implement K-Core with only a priority update enqueue operation, we need to add two features to the algorithm. First, we need to add an array manually tracking the priority of every object in our queue, in this case, the vertices of our graph. Second, we need to add an early exit condition. Because we are enqueuing vertices instead of updating them whenever a priority changes, some of our dequeues will be out of date and should be skipped. These early exiting iterations do nothing, and they might as well not have run at all, so we call them moot. Supporting priority updates will allow us to avoid executing these early exiting moot tasks. To see why we want to do this, let's walk through the execution of K-Core in a bit more detail. In here, we have our updatable priority queues task graph on the right, which will be much like the one we just saw. And a swarm-like priority queues task graph is on the left. We will enqueue all of our vertices according to their degrees. So let's see what happens when we dequeue just vertex E. We can see that in our swarm-like schedule on the left, we've added a new task for vertex D and created a dependence on the old one, which will tell it to early exit. In our updatable queue, on the other hand, we have moved that task from priority 3 to priority 2. Now, when we'll dequeue vertex F, the same thing will happen again. Our swarm-like queue now has 3 separate tasks just for vertex D, while our updatable queue still has only 1. Now, when we dequeue vertex D, the same thing happens for vertex C. We have 2 tasks for vertex C in our swarm-like queue and 1 in our updatable queue. So that's all of our priority updates in this graph. So what have we learned from this? Well, our swarm-like queue now has 3 more tasks than our updatable queue did. These moot tasks do not need to run at all, but Swarm is going to run them anyways. The question is, how many of these moot tasks are there on a real graph with a real running for real? And the answer is, moot tasks tend to outnumber the real ones. Here we track the number of moot tasks compared to useful ones across some of our benchmarks. The y-axis here is the number of moot tasks divided by useful tasks on a log scale with benchmarks on the x-axis. Note that some of our benchmarks have tens of moot tasks for every single useful one. This makes some sense when we think about it. Every priority update creates a moot task, and these algorithms will usually dequeue a vertex, then update all of its neighbors. So we can expect our moot tasks to outnumber our useful ones by a factor up to the average degree of our graph. In a nutshell, most tasks are moot. Now that we've understand Swarm's issue with moot tasks, we'll introduce our solution, the Hive architecture, a hardware-software interface which extends Swarm to speculate on priority updates. We will start with Hive's execution model, which we will explain by showing you the Hive code for K-Core. As you can see, the task is very similar to our K-Core code, sequential code. The only thing that's really changed is the scheduler interface. What we care about here is the call to Hive update. We have 3 components to this update call. First, we have a pointer to the task that we're going to execute. Second, we have the object. Objects are how Hive recognizes as individual tasks and finds them later to update them. They generally correspond to our input data in some way. In this case, the object is a vertex. Each object is a vertex in our graph. And finally, we have a timestamp. Hive's tasks are timestamp ordered and will appear to execute in order. A call to Hive update will bind a task with a given timestamp into the object table, which schedules it to run. All these tasks would appear to execute in timestamp order regardless of their object. Just like Swarm here. The trick is what happens when we call update on an occupied object. Let's see what happens here when Hive runs the task for vertex E. We are going to call Hive update with object D and timestamp 2, but D already has a task in the object table. So when we call the update for an object which already contains a task, the old task is moot. Since moot tasks don't have to run, we remove the old task from the schedule when we replace it in the object table. Because Hive removes the old task from the schedule when it was replaced, it does not waste time or queue space on moot tasks. Now, we've just explained a basic update here, but Hive can do some more complex operations too. Hive supports several different types of update in order to express all the different update patterns we find in our benchmarks. We include a full analysis, including code examples of all these patterns in the paper. One thing to note here is that some of these benchmarks don't even include priority queues in their sequential implementations. They just use for loops, but they still benefit from Hive's dynamic scheduling. Now that we've learned about Hive's execution model, which is a sequential schedule with updates, but Hive is not really a sequential schedule. It uses speculation to be a parallel schedule with updates. Let's learn about exactly what it is that we are speculating on. In order to run tasks in parallel, Hive speculates eagerly, which means that every task in its schedule can be run at any time. We are speculating that we will not see any earlier timestamp writes to the data our task is reading, that the parent task which created this one will not be aborted, and that no earlier task will send updates to replace this task. Our data and control speculation is the same as swarms, so I won't discuss them here, but our speculation on updates is new. The dependence created when a task update places another task using update is what we call a scheduler carried dependence. The scheduler dependence is not truly unique to priority queues, but you also won't find it in most straight line code. While we are naming the dependence here, we find it in some very old code called self-modifying code, where one instruction can overwrite another, creating a dependence which is neither a data dependence nor a control dependence. When a task in a priority queue updates an object in the queue, replacing the currently scheduled task, the dependence created is also a scheduler dependence. While we can predicate scheduler dependencies into data and control, doing so leaves moot tasks in our queues, as we saw with Swarm. Hive recognizes and speculates on scheduler dependencies directly, allowing us to process them immediately. This uses a technique we call the task versioning. Task versioning and mootness detection are to scheduler dependencies what data versioning and conflict detection are for data dependencies. There are three main ideas behind task versioning. First, we maintain multiple versions of any task subject to updates, one non-speculative and some number of speculative versions. Of these speculative task versions, at most one is speculatively useful. The others are speculatively moot. These speculatively moot task versions are not eligible to dequeue and will not accumulate speculative state. And when these mootness of these speculatively moot versions becomes non-speculative, we will discard them immediately. In addition to versioning, our conflict detection or mootness detection is quite simple. We simply compare the timestamps of the tasks which created each version in order to determine which one is most recent and not speculatively moot. By marking task versions as speculatively moot, Hive is able to avoid running moot tasks and avoid creating expensive read sets, saving on speculative state. Now let's talk the hardware. We build Hive by extending the Swarm architecture. Swarm is based on a tiled multicore and adds a task unit to each tile. The Swarm task unit contains large task queues and storage for a huge amount of speculative state. Swarm's main features are data dependence detection integrated into its coherence protocol and storage for these many speculative tasks. First off, Hive extends the Swarm task descriptor with parent timestamps and an object ID, which allows it to match up to detect mootness. Hive also adds a small content addressable memory we call the object map, which allows us to quickly look up tasks by their object ID. Second, Hive adds an in-memory object table, which stores metadata for all Hive objects. Overall, Hive requires a 9% increase to the area of the Swarm task unit, which itself was less than 3% the area of a modern processor. So this is a very small area cost. Now that we've explained how Hive works, we'll evaluate it against both Swarm and a conventional multicore. We measure Hive's performance by modifying the open source Swarm simulator to support Hive's updates and scheduler dependencies, and we test 9 benchmarks on systems with up to 256 cores. On these irregularly parallel benchmarks, software parallelism struggles to scale beyond a few tens of times speedup, even at 256 cores. Swarm does a bit better. It comes close to linear speedups at 256 cores, and even achieves superlinear speedups on a couple of the benchmarks. Swarm speedups come from being able to speculate across priorities with tiny tasks which rarely abort and can make full use of a large multi-core resources. On some benchmarks, though, we see that Swarm speedups are plateauing by 256. Hive always outperforms Swarm. Hive achieves speedups of up to 2.8x over Swarm at 256 cores and is superlinear on more benchmarks than Swarm is. Now, let's talk about why. We break down the cycles that both Swarm and Hive spend on executing tasks, managing their queues, and waiting for work or space. While we present a full analysis per application in our paper, let's observe some overall trends right now. First off, Hive just plain does less work than Swarm does. The green bars here represent cycles as core spends executing a task which eventually commits. Hive is always reducing this number, sometimes by almost 40%. Second, we can see that Hive gets more out of its queues than Swarm does. The orange here represents cycles spent spilling tasks to memory, and the brown represents cycles spent stalling once Swarm runs out of space for more speculative state. Hive produces even larger savings here than it did for committed cycles, and almost completely eliminates stall and spill cycles for some benchmarks. In summary, we have shown that ordered algorithms make heavy use of priority updates, and that the dependencies created by these updates are unusual and require their own speculation. By speculating on these priority updates, Hive is able to unlock more parallelism than any previous architecture. Thank you for your attention and your questions.
Thank you very much. One question, please, because we are running out of time. Okay.
Sure. In order to achieve the performance gains that you saw, how fast should your task scheduling hardware be over the classic software implementation?
By how fast? So how much fast? So if I understood you, you're asking how much faster is our task scheduling hardware compared to software task scheduling? So software task scheduling is going to be based on a software data structure of some sort, which is going to create many dependencies, and also many operations. Our task scheduling hardware is implemented with a custom instruction, so it is very fast. The arguments are all passed through registers, and after that, it is the NQ and DQ are very much decoupled. So the latency of scheduling something is very low, and many tasks are available to be run at any time. Compared to software, which requires some amount of synchronization, you are looking at orders of magnitude speed up because the scheduling itself is hardware accelerated. We can often see speed ups even at one core as a result of the scheduling being hardware accelerated as opposed to purely in software.
Thank you very much, and let's take the rest of the question offline. Thank you. Thank you all.